So one extra complication, z-scores. Now, most of the data that we've been dealing with has been based on looking at one set of data. So one situation. We talked about the guy with a bunch of dogs that we wanted to know what the mean was for his weight of the dogs. You could do like a bunch of test scores in a classroom. Where did you fall on the score for the mean average? Were you above average? Were you below average? And we talked about standard deviations and how that kind of separates this distribution of data into chunks where we can say, well, 68% of you guys are going to be one standard deviation below or above the mean, and then it goes from there. There's more details on that in another video, but the idea is all of this stuff talked about one set of data. So it's kind of hard to take that and then compare it to another set of data. Like say, for example, if you were in class and you went, okay, I want to know how I compared with everybody else on my last English test. That would be good. But then you'd want to know, well, how did I compare with everybody else on my last math test? But then those are two different scores, two different distributions, and it's pretty hard to just look at one and compare it directly to the other because the values are different. So what we do in cases like that, where we want to take two different sets of data and compare them, is we use what's called z-scores. So z-scores are how many standard deviations from the mean is any particular piece of information. So that means that now we're kind of not looking at all those specific numbers you put along the bottom of your graph or your distribution graph when you're figuring them out. You're really looking within here and going, okay, where does it fall in terms of standard deviations? Is it one standard deviation away? Is it two? Whatever. So when we have two separate sets of data that we want to compare, we use our z-scores to do that. Now the formula for a z-score is just the number that you're looking at, so your individual test score, for example, minus the average, the mean. So that's going to say how much you deviate from the mean right there. And then divide it from the standard deviation, so how much most of you were away from the mean. And then that's going to give you where you fall on the graph. So to give you an example of that, we're looking at page 255 in your textbook. And it's just talking about Haley. She's a runner, and there's two different races. So I'm just going to do a quick little table here and show you what I mean. Obviously, these are the numbers that we're interested in. So the first run she did in Vancouver, the second run she did in Lake Louise, and we can just fill in her numbers for these. So the average, the club mean for, the club mean for each one of these, for Vancouver it's 25.75, and for Lake Louise is 25.57. These guys are really going out there with their numbers. And then the standard deviation for the clubs was 0.62 here and 0.60. So they're trying to keep the numbers close so you can't guess at the answer. Now Haley's run time, so that would be X, right? Her specific run time compared to the averages is 24.95 here and 24.77 here. So now we have two different sets of mean, standard deviation, and the actual number. So we can work out for her which one she did a better job of. So for Vancouver, we've got the formula, Z equals X minus mu over, I don't even know what that symbol is, you'd have to look it up. So I'm just going to put in the values. X is 24.95 minus the average, which is 25.75, all over standard deviation, which is 0.62. So I'm just filling in my numbers that they gave me, and I can work out my answer. So it turns out that if I I subtract these guys and divide by 0.62, her z-score here is equal to negative 1.290. So what that means is she's below average, which in this case is good because it's a running time. But here's 1. So 1.290 would be right around in here. Right? Because this is 1 and this is 2. So 1.290 is about 1.3, about 1 1/3. So I'm just going to put 1.290 up there to keep track of it. Now, I'm a little out of space, so I'm going to erase this. And I'll use the blue pen to do Lake Louise. Same thing. Z equals x minus mu over standard deviation. So I'm going to use the x value for Lake Louise, which is 24.77, subtract the mean, which is 25.57, divide by the standard deviation. And I should subtract those guys, divide by that, and I will end up with negative 1.3 forever. 1.33333. So even though they're close, which is why they use those close numbers, this one's more toward the 2. So if I were to write this line, it would be a little more. Well, it's actually exactly 1 1/3. So that guy is 1.3 forever. So compared to everybody else, because I mean, you look at runs, you might have different terrain, you might have different footing, all different kinds of things, but this just equalizes everything, because now it's like, okay, compared to the average, how did she do? Which one did she do better on? Well, remembering that this is a race, so she's going to want to do the best she can in terms of this way, right? She was faster than the average on the Lake Louise race. So that means her time's better for Lake Louise.